In today's video, we are going to look at some modeling with exponential and logarithmic functions. We're going to work on 3 problems. Here's the first one. A couple invests $8,000 in a bond fund. The expected yield is 4.5% and the earnings are reinvested monthly. Part A. Use the formula A is equal to P times 1 plus R over N to the N times T to write a model representing the amount A in dollars in the account after T years. The value R is the interest rate and N is the number of times interest is compounded per year. Okay, so we have seen this formula before. We know that P stands for principal, which is the initial amount, whether it is an investment or it's a loan, but it's the amount at the beginning. R is the interest rate and it's a number of periods. So reading the problem, I see that the initial amount is 8,000, so that's going to be your P. The expected yield is 4.5%. This is going to be the interest rate. And reinvested monthly, so this is going to show that our period is going to be 12 because there are 12 months in a year. So we're going to plug all the values in to calculate the balance in the account, which is A, after T years. So that's 8,000 times 1 plus, R is 4.5%, but we must convert to a decimal number, which is 0.045. Divide by N is 12 to the 12 times T. Okay, now that we have the model, we are going to try to do part B and C. Determine how long it'll take the initial investment to double. Okay, so right now the initial investment is 8,000. Double means 8,000 times 2, which is going to be 16,000. And we want to round the answer to 1 decimal place. So we're going to plug in A, which is the amount that we want to have after T number of years. So that's going to be the future values that we wish to have. Okay, and then 8,000 times 1 plus 0.045 over 12, and then to the 12t. Our goal is to calculate how long, so we need to find this t. Now this is an exponential equation, which means to solve this, we're going to have to isolate the exponential expression, which is this guy right here. So to do that, we're going to divide both sides by 8,000 first. So let's divide both sides by 8,000. So this will cancel. On this side, we'll have 2. And then we'll go ahead and calculate this guy right here. 1 plus 0.045 divided by 12. Following the order of operations, you must do 0.045 divided by 12 first, and then add 1 to it. And when you do that, you are going to get 1.00375. Now I know that's a lot of digits, and the problem says round to 1 decimal place, but I will save the rounding until the end. So we try to include as many digits as we can right now. And then to the 12t. So now that this exponential expression is isolated, we can take the log of both sides. So either you can use the log base 10 or log base e. Either one of them will be doable on the calculator. Okay, so we have this. Using the power rule, on the right side, we can move this 12t to the front, and that's going to give us 12t times log of 1.00375. Now remember, all these logs here, they are just constants. If you put them on the calculator, they're constants. And our goal is to get this t by itself. So really we need to get rid of the 12 and the log of 1.00375 to get that t by itself. So I'm going to divide both sides by 12 log of 1.00375. And we're going to write the same thing over here. Okay, so on this side, we can see that things cancel out. So you're left with t, which is exactly what we want. So t is equal to log of 2 divided by that. Use your calculator. That will give us approximately 15.4 and round to 1 decimal place. And this will be years. That's the unit. Okay, so it means that it'll take 15.4 years for the 8,000 to double to 16,000 in this bond fund. Part C, determine how long it'll take 8,000 compounded monthly at 6% to double. So this time we have a different interest rate. So we're going to have to rewrite our model. Again, we want it to be double after certain period. So we're going to write 16,000, which is the amount that we want in the future, is equal to 8,000 as still the initial amount. And 1 plus, this time is going to be 6%, so 0.06. Divide by monthly still, so divide by 12 to the 12 times t. Okay, so we're going to solve again, very similar. We're going to divide both sides by 8,000. Now remember that this exponent 12 to the t only belongs to this base. It doesn't belong to 8,000 at all. Therefore, we can divide both sides by 8,000 to get rid of it. Okay, so 2 is equal to 1 plus 0.06 over 12 divided by 12t. We will then calculate this number in the parentheses. That's 1.005 to the 12t. And then we can take the log of both sides. Again, you can use log base 10 or log base e. I'm just going to use log base 10. Using the power rule, we move the 12t to the front. And we'll end up with this. And on this side is log of 2. Then we just divide both sides by 12 log of 1.005. 12 log of 1.005. 12 will cancel, log of 1.005 will cancel. That will leave us t, which is what we want to isolate. And t is equal to, that's going to be approximately 11.6 years, round to 1 decimal place. Okay, so you could see an example on compound interest involving exponential equations. Let's look at number 2. Solve an equation for a specified variable. Part A, a short-term model to predict the U.S. population P is equal to 310 e to the 0.00965 t, where t is the number of years since 2010. Solve for t. So you can see that these exponential functions not only apply to compound interest, but also U.S. population. And then eventually in part B, you're going to say in geology, and part C is astronomy. So lots of different fields use exponential functions. So let's solve for t. So P is equal to 310 e to the 0.00965 t. Now, you're not going to get t as a constant at the end because there are 2 variables involved. The best thing you can get is just t in terms of p in your answer. Okay, so our goal is to solve for t. We want to be able to move that t to the front. So we are going to isolate the exponential expression first, which is e to this whole exponent. So to isolate that, I'm going to divide both sides by 310. Okay, and then on the right, I have e to the 0.00965 t, and then p over 310. I will then take the log of both sides now. This time I am going to use natural log ln, simply because there's a base e involved, and I know that on the right side here, I can use one of the basic properties, or the power property where you can move this exponent to the front, but ln e is 1. So it's really just give you the exponent. So this will become ln p over 310 is equal to 0.00965 t. And now we can get t by itself just by getting rid of that constant in front of it. So divide both sides by that constant. So at the end, t is equal to, now I see a quotient here and I know I can break it down by using the quotient property. So that's ln p minus ln 310 and then over 0.00965. And that right there is our answer for t in terms of p. So part B, p is equal to 100 e to the kx minus 100 and solve for x. Okay, so our goal is to get this x by itself. And first thing I want to do is to isolate that e to the kx there. Just e to the kx. So I need to get rid of that 100 and then this 100. So one thing at a time. First, we're going to add 100 to both sides. So that's p plus 100 equals 100 e to the kx. Now we can divide both sides by 100 so that we can get rid of the other 100 there. So that's e to the kx. And then on this side, we're just going to keep it this way. All right, now I see base e, so we can take the natural log of both sides. So ln p plus 100 over 100. Okay, on the right side, using either one of the basic property or the power property, you can move that kx to the front and then times ln e, but ln e is just 1, so it's really just kx. And then on this side, I see a quotient, put that in parentheses. I see a quotient, so I can rewrite that as using the quotient property. So that's ln of p plus 100 minus ln of 100. Okay, don't lose your goal in sight here. We're still trying to solve for x, so we need to get rid of that k. So we'll just divide both sides by that k. So the final answer would be ln p plus 100 minus ln 100, and then all over that k. Part C, this one is used in astronomy. So we have L is equal to 8.8 plus 5.1 log of D, solve for D. Okay, so this is a log, an equation involved logarithms. So first one that we've seen in this section here. Our goal is to get that log by itself. But same with the exponential equation, we want to isolate the log first, then we'll go from there. So we want to isolate this log here. So that means we're going to need to get rid of that 8.8 and that 5.1. So let's get rid of the 8.8 first. So that's L minus 8.8 is equal to 5.1 log of D. And then divide both sides by 5.1 to get rid of that 5.1. Okay, so then this will cancel. That should say 8.8 here. On this side, we should just have log of D. So there's only one log that I see, so I can't really use the equivalence property. However, I can use the definition, the converting it to an exponential equation. So this is log base 10. Okay, I mean, if it helps, you can swap the position of these two. So the log would be on the left, and then the other one would be on the right. And then you can use that arrow trick to write the exponential equation. So that's going to be 10 to the L minus 8.8 over 5.1 is equal to D. Well, what do you know? We just got D by itself. So that means we're done. This is the answer. Our final problem today, we are going to look at continuous compounding. Suppose that 15,000 is invested, and at the end of 3 years, the value of the account at 19,356.92. Use the model A is equal to P to the RT to determine the average rate of return R under continuous compounding. So this time, we are not looking for the time years, a number of years. We're going to look for the rate R. So let's set it up. Okay, so do we know A? A is the amount that we want to be at the end of the period. And that amount is 19,356.92, and that's at the end of 3 years. Okay, P is the initial amount invested, so that's $15,000. E, R, that's what we're trying to find, and T is 3. Okay, so this is an exponential equation again. We are going to isolate E to the R times 3 first by dividing both sides by 15,000. Now, right now, if I do 19,356.92 divided by 15,000, I might get a number that's not very nice. So I'm going to leave it until the very end, and then that way we avoid rounding as much as possible. So we know this side, 15,000 is going to cancel. We know E, I'm going to write 3 times R. And then, again, I'm going to keep this exactly the same. We'll divide at the end. Okay, so I see a base E, so I'm going to take the natural log of both sides. All right, so on the right side, I should have 3R. And then on this side, I still have this same guy here. Okay, our goal is to get R by itself. So we just have to divide both sides by 3. So R is equal to that whole complicated looking thing, but it's just a constant. There are all numbers there, no variable there. Okay, divide the whole thing by 3. So when you substitute this in your calculator, just type natural log of this. We're going to put this in parentheses and then divide by 3. So that's going to give you 0.085. And because it is an interest rate, we're going to have to convert it to a percent. That's going to be 8.5%. So there is the missing interest rate.